Yijing YAN from University of Science and Technology. We will talk about quantum mechanics of open systems in 3 classes of class.
Organizers, my good friends, Dr. Yijing YAN invite me to come here. Although this workshop is computational chemistry, and I'm talking slightly different, from different angle, and this is called purely just fundamental theoretical development. And the 3 classes of the bus, I will just talk about the 3 classes. One class is phonon bus. And phonon bus, you know, just each phonon state has occupation number 0, 1, 2, 3, all integers. And also 2 phonons actually commute. Okay. And now the second class of bus is electrons. Electron, for each electronic state, occupation number only 0 and 1. And just 2 electron states and 2 electrons and can just anti-permute. Okay, commutation is minus sign. And the other just class of the system is 2-level, like excitonic systems. Each exciton state have occupation number 0 and 1. But 2 exciton is permute, like bosons. Okay, these 3 classes. I want to have a unified theory, and this can cover all these 3 classes of bus. And this is going to address in terms of dissipaton equation motion. I will describe dissipatons. Now, just this theory is non-perturbative and also work for non-Markovian environment. And also, this is not only for the reduced system dynamics. It's usually the quantum mechanics for open system only address the dynamics of the reduced system. This is also can partially address, at least, is for just bus dynamics. I will going to describe, and also going to have an external field applied either on system or both on system and also on the environment. I will describe the situation to say it. And some just preliminary just how just this advanced just development. We know just isolate systems that satisfy shading equations or these are total density operators described by Van Neumann equations. This is all people know it. For the reduced system density metric is defined just by total density metrics that trace over all bounded degree of freedom. And bounded degree of freedom you consider is 10 to the 23. Really basically trigonometrically a huge number of the degree of freedom you trace off, and the remaining is fewer interested in the reduced system degree of freedom, much fewer, and this is going to have energy exchange. And also matter can exchange, like electron can put in and out of the system and environment. Also important for quantum mechanics is a phase. Okay, phase is related to basically quantum information. And this is going to introduce so-called irreversibilities, like the second law of thermodynamics is going to define just entropy and free energies, or you can basically calculate using the theory you can develop from there. And how does it evolve in time? We only know just the evolved time of total density metric is a Van Neumann equation. And what is the exact equation motion for these reduced density metrics? Now, history, basically, the interesting thing, just you can start with Einstein's 1905. This is Brownian motions and introduced there, and it's important, and fluctuation dissipation theorem. And basically, people is Landry equations, etc. to know how to friction, and this is going to give you dissipation, and this is also the correlation like environment. You need to consider fluctuation. Okay, this is exact the proof of the fluctuation dissipation theory by the 1951, and this is going to use it again, and also this developed quantum mass equations, basically all these perturbative theories and Markovian theories, assuming the system bus coupling is weak and also is Markovian processes, and also Candela-Lagat equations. So the bus is not just ordinarily just Markovian, and this is basically have delta function, also have a delta dot, because any function that have a symmetry part approximate by the symmetry reason, this is delta function, and delta anti-symmetric is delta dot, and this is also related to fluctuation dissipation theory, but in classical prospect. If I have time, I also talk about this one. Is related to our further new development. Okay, exact theory, and this is basically start with Gaussian bars. Actually, this is for phonon bars. Okay, for phonon bars, this is part integral inference functional formalism. Is the first formalism established is 1963 by Feynman-Vernon, so-called Feynman-Vernon inference functional theory. And for this is second quantization of this path integral formalism is basically introduced called Grassmann variables. Okay, under this under just representation and fermion particles under representation is not C number. Okay, because fermion just satisfies xy equals minus yx instead of the both of xy equal to yx. That number called C number. Fermion, this is called Grassmann number. That's xy times x times y equals minus y times x. Okay, this is second quantization introduced there, and this is part integral formula and the application. And for numerical, just efficiency is very low. Okay. People like to solve shifting equations, the equation of motion, differential equations, and convert this one, part integral based, and convert to equation of motion. This is called hierarchical equation of motion. And for bosonic bars, it's initially just start with Kubo and his that time his PhD student, and also important thing just to mention, Zhu Shao is based on slightly different method, basically derive exact equation. There are many ways to do it. And for fermionic system, this equation motion actually we developed this a few years ago. But that time is no available formalism for the exact formalism for spin or two-level systems. Okay. So now just give the basic feature of this hierarchical equation motion. The base formalism is called first tier is reduced density operators. Okay, and if you cut to the first tier, zero tier is a reduced system density operator. If you cut to just a first tier, it's called usually like quantum master equations, etc. However, what is physical meaning of other just density operators? In that time we called auxiliary density operators. We don't know what is physical meaning. And more recently, and just new theory developed, is basically go through the path integral formalism. Okay, we directly go to the differential equation formalism. When with Van equations, you can derive the very simple equations, basically the same, and but we can go much further. And this is first just this physical meaning. Now we know it is called dissipatons. Okay, describe the fast dynamics. Not only describe system dynamics, but also can describe the bus dynamics. And also, this is here, now we classify as a number of the dissipatons, like a couple cluster systems. The whole theory is like quantum mechanics for open system in full configuration space. Okay. Okay, the development is go slightly just step by step. Start with Van equations. Okay, and you just first consider it's a system bus coupling. This is characterized of the system operators and bus operators. Okay, and the theory just start with describe the bus operators only. Okay, this is considered is non-interacting bus. Okay, it can be characterized by so-called bus just hybridization functions. Okay, this is commutator and the average is defined for phonon bus, and this is anti-commutator and the average is considered for electron exciton bus. Okay, this describe basically is non-interacting itself. This is occupation number can be 0, 1 to any numbers, and this observation can be just 0 and 1 only. Okay, and this is just applied to the quantum fluctuation dissipation theory. It's exactly connect to the correlation functions and quantum mechanics theories. And this is to say, if you know these correlation functions, and you know how this affect on the systems. Okay, and then now just we can use the mathematical approach, parameterize. This is J as such that this is correlation can be expanded to exponentials, series exponentials. And this branching later we can say how this is related to our theoretical development. And this each just a component of exponents component we're going to call dissipatons. We're going to know. And okay, so the dissipatons basically is related to this each individual just exponents, and all just we need just this total dissipaton decomposition. After that, this is reproduce these correlation functions. Okay, this is easy to do it. Okay, and how does this is dissipaton and going to interest? Okay, and now just dynamic variable we define here is called multi-dissipaton density operators. This is like a total density operators, and this is total n just dissipatons. And n can be 0, can be 1, etc. And when n equal to 0, this exactly just reduced density operators. And n to 1, just 1 dissipaton participate. 2, that means 2 dissipatons, like a couple clusters. An important thing here, we put small circle. This is irreducible dissipatons. Okay, this is irreducible dissipaton just have simple relations. If you change this Fermion dissipaton, you change swap just this permutation, give you minus sign. Okay, it's irreducible, and this is for phonon bars. This is basically permute. We not bring the minus sign. And for excitons, okay, spin bars, this itself is not go to just occupation go to more than 2. But if for J not equal to J prime, this is permute, like bosons. This describe this, all these simple things describe everything. All these 3 classes of dissipatons. Okay, now you apply just Newton fundamental equations to this equation. Basically, you make a dot here. Then we have like the first term is go to Lewisian, and second term go to these exponential terms because of the single exponent correlations. Okay, this is why this one, because this is like a Heisenberg equations, Heisenberg equation motion. This is like a derivative. Okay, this derivative just a single exponential give itself. Now you go to the third term. Third term just basically just Wu. Yesterday, just the last talk was described as a Wick theorem. And this Wick theorem applied here as that way. The system bus Hamiltonian now just decompose of dissipatons. Now for each dissipaton you put there, you have left action, and this one we have n irreducible already, and plus 1 is still remain to be reduced. Okay? And this reduced series, just this is go to the n plus 1, and this is contraction. Okay? Immediately, you can obtain the equation, the n plus 1, you go to this term, and n minus 1 go to this term. And this is immediately built up with whole exact equations, basically without any approximation. And this is also unified theory for the electron, phonon, and spin bars. And this is basically it's a hybrid system bath dynamics. Okay, this is established of the quantum mechanics of the open systems, and this original formula established basically is an analogy to the full CI and also couple cluster method. Okay, some benchmark evaluations, and basically I just go over just these 3 classes of bars, like 2-dimensional spectroscopies of some model biological FMO proteins. Okay, this is you need to calculate nominal response functions. Basically, you need 3 times just correlation function, have 3 times variables, and you can have a picture of Heisenberg picture. Okay, you can have propagate the total density operator now in the space. It's not in ordinary just a Lewis space, now in a dissipaton dynamic space. Okay, you need to consider the whole dissipaton, the dynamic space. Okay, this is can have a Shannon picture, and this is can have a Heisenberg pictures. Basically, there are three just time correlation function, 3 time variables. You can have a 2 time and plus 1 time. Okay, the dimension like 3 time, 3 dimension become 2 plus 1 dimension, and calculation much more efficient. For example, for this total, this system have 29 system levels, and converges is total distinguished dissipaton, 14 dissipatons, a large cluster of dissipaton, we have 4 clusters, and it's many combinations, like full CI calculations, and this is for each frame, like a CPU, only like a very just simple CPU, like my office is a cheap CPU, like only 30 minutes for each with 3 dimensions. So this is quite efficient. And this is previously we talked about just phonon bars. Okay, this is now this is for second thing we describe exciton bars. This is a case we consider is a double layer graphenes, and we not apply the gate voltage, and this band gap is not open like a Dirac cone there, and this is less useful. However, you apply the gate voltage, and this band gap is open. Okay, and that opened actually can be tuned by external applied gate voltage. This is many applications. Okay, the system here actually is bilayer lattice phonons. This is optically active, discrete. This is only not only activated, this band gap also activated with the lattice phonon. Okay, before applying this lattice gate voltage, the phonon is not active. And also, the bus now is considered as 2 level. Okay, continuous excitonic band edge gap is 2 level. That is also optically active. Okay, so this is optically active. This is also optically active. And discrete level is coupled to continuous level. This is very famous phenomenon called Fano resonance. Okay, Fano resonance, and then we can just system is now harmonic systems, and bus is a 2-level bus. We can calculate exactly without any approximation. And here we calculate like a Fano turnovers. This is take off the background. Fano just like the dip and become the peak, and also this is basically depends on external the gate voltage and controlled. And this is still in preparation, and it's going to publish soon. And this can reproduce experiments very well. And now just also talk about this electronic bus. This is Fermionic bus. This is considered about current go in and out, okay, of the system environment, and also you can calculate the current correlation functions. And current, you emphasize current here is bus. Just you measure the current actually for the and current goes throughout from systems, basically environment just properties, okay? And also you can calculate strong correlation systems. How much time I have? Still have 10 minutes? Okay. Just basically this is strong correlation systems. You consider actually is like impurity Anderson models. You consider single impurity Anderson models. And the state is electron state is buried below just Fermi energies. Okay, and this is after double occupation, because Coulomb interaction double occupation, the energy can be higher. And this is in between have energy gap. It's a Fermi energy gap, and this Fermi energy gap is only be just visible when just it's a very low temperature below just a Caldon temperature, and the spectrum signature there is a very sharp peak. Okay, very sharp peak. And here just a recalculation of just how many clusters. Okay, the dissipaton clusters this is L equal to 1, like quantum mass equations, and this is given very just almost just qualitatively incorrect, okay, qualitatively wrong, and this is converges as L3, L4, L5, and converges very fast. An important thing here, and for the Hubble peak, okay, the peak for these real applications and can just converge very fast, okay. Even just like 2 or 3 is converges, okay. 3 converges, and this quantum peak is much slower, okay. Another thing, just this one we calculate just time-dependent voltage. Okay, this will not explain too much. Basically, this is you put this shape is typical. Is only for quantum in the quantum regime. Okay, and this is current correlation functions. Okay, the strong correlation systems. We will also calculate like Hubble models. Is the whole just Hubble models like lattice. They have contribution of tight bindings. Tight binding basically this is contribute for electron the transfers or Coulomb interactions for each side. Okay, this Coulomb for each side, and this is responsible for magnetic just properties. Okay, this is can be mapped to this Anderson impurity model. Okay, basically you have impurities contains Coulomb interactions. Okay, and the environment is only tight bindings. Okay, and the reason we can to map this one, basically you do iterations, dynamic mean fields. You calculate this impurity, the spectrums, and you make the spectrum like an environment, and you put back, make this converges, such that your system is same as the environment. Okay, therefore Coulomb coupling basically is bring up to the whole systems. Okay. That's make a convergence. And we calculate Mott transitions. Okay, this is called a new theory, and this dynamic mean field put together, and also this by stabilities. All these benchmark evaluation being just calculated by just most advanced previous studies, and our approach actually is much more advantages. Okay. I have no time just to talk how to optimize this one. As a basically principle just says this is considered as a full CI, and we also have a minimum basis set problems, and not only have a minimum basis set, and also how we can just because of this construction, basically it's based on this dissipaton decomposition. Okay, exponential forms. This is in terms of the quantum mechanics. This is basically very elementary algebra. We know this minimize this K, and we also can put in the residues. Okay, this minimize this K, and we'll not go to that detail. Basically, just say generally just multiplier expansion of the Fermi function or both function is terribly just bad. Okay, and this is easier way to is a Padilla approximate. Okay, and Padilla approximate and basically need to develop just accurate, very accurate the algebra to evaluate the Padilla type of the poles and coefficients, and we can do it. And the paper we published and a few years ago, and how good it is a Padilla and how bad is a multipliers. Okay, this green line is multipliers. This is the y-axis is accuracy length. Okay, you see just a new just a Padilla spectrum decomposition one, and this is accuracy length is increased dramatically, and as a n number of n is basically related to number of dissipatons we're going to involve. And this is a blue line, and it's the green line even below this blue line. Okay, if you have this n equal to 10, for example, and this is accuracy length is already several hundred, but it's if you go to just Padilla, you need to go to under 100. Okay, increase dramatically because you know the full CI and number of the dissipatons is dramatically power law dependent. So you can drop this, you can do the calculation easily. And also, we talk about is a residues, okay? This is like a basis set. So what is the fact outside the basis set? How you can bring it in, okay? This is basically, we can use the divergence of both the functions, okay? Both function itself is not divergence, but you can have a Padilla constant instead of just a different Padilla. This is n polynomials in numerators and n polynomials in denominators. Okay, this is going to give you the divergence, and we're going to produce like a delta dot type of residual correlation functions. And this residual correlation function we call Cadetta-Lapet residual function can be incorporated in this formalism. Okay, and also this is accuracy controllable. Okay, this is that we have optimized the theory with minimum just basis set. Okay, yesterday just I should also talk about this minimum basis set problem. This is the same thing. And also for the couple of clusters, okay, what is size of clusters matters physically, and this is we also can have a control of it. So this is basically we have a minimum basis set and also control just physically relevant just cluster size, and this is we can do it. Okay, basically. Okay, as a brief summary. Summary just a fundamental theory for open quantity systems, and this is dynamics. Actually, is can describe hybrid system and bus dynamics. Okay, not only system dynamics. And this is universal and friendly, used for various studies, including strongly correlated electron and phonon and exciton systems. This is can calculate linear and nonlinear response functions and both equilibrium and non-equilibrium. Non-equilibrium just means apply voltage, and you can consider current under current flow conditions. And this is very accurate, also efficient, and this is problem now is only work for finite temperatures and cannot work for zero temperatures. Because of this, we use the exponential expansions. Okay, and finally, we'd like to thank my fellow. The collaborators is Professor Zheng Xiao and Yijing YAN and Richard. All used to be my postdoc or student, and now it's all just independent work, and it's especially Zheng Xiao basically developed all just a numerical method. We have many discussions, and also thanks for your attention.
Simple question first. It's a very interesting talk. My question is, we know that a system coupling with a bus can lead to lower phases to the system. And, if a system is coupled to a bus, and this will brought lower phases to the system, quantum phases to the system itself.
Sure.
And according to your method, you can probe the dynamics of the bus itself. So can this method provide more information about the phases of
this is just an example I present there, and that's including the full spectrum of the Fano spectrum, including system bus. Why this is system the peak can become dip and become peak, this is due to interference.
Yeah.
You say it's due to the phase.
Yeah, because I think in some cases the phase transition of the system itself is very controversial.
Sure.
And also the order of the phase transition. So
yeah, this is a Mott transition. I just do not have time to explain just more. Basically, phase transitions, by stabilities all appear there. Maybe if I stop there. This is considered as a lattice. This is demonstrated with this is phase transition temperatures, and this is metal, just like have a band gap. It's a continuous, just have a spectrum density. Okay, it is zero frequencies. Okay, so this is metal, and this is become insulated, band gap is closed, just a low density there. And this is another calculations. Basically, consider how you prepare it. If you fix this coulomb coupling strength, if you just go to iteration strength, you see decrease U, just from the top to from up level to this one, and you can give just this line shape. If you increase U to reach this value, and you can get different. It's a bistable. This is definitely you have this phase interference, and also this depends how you prepare it, and this bistability is also help